I'm going to start recording, share the screen. And so the problem, this is the problem, right?
Yes.
The pin is confined to move vertical or horizontal if the slotted arm causing A to move downward VA determine VB. Okay. So this is a part of geometrical analysis, right?
Mm-hmm.
Or as we call it, absolute motion analysis. D is a constant value, right?
Yeah.
H is a constant value, right? Now, let's say this angle is theta. How much is this angle?
Probably the same.
No. If this is theta and this is 90, this is 90 minus theta. So technically this angle is theta, right? You follow? This is just the geometry. The whole thing is 180, right?
Yeah.
You took 90, this guy plus this guy are going to be 90. So if theta plus this is 90 and this plus this is 90, so this is going to be theta, this angle. Make sense? Now, if you look at this, I can relate y of A to angle theta with the tan, cotan, sine, cosine theta, right? For example, if this is theta, right, y is going to be d times cotan theta, right? You follow?
So that's how you're going to relate y to d.
Technically, d is a constant. I relate y to theta. You remember? For this part of the chapter, we said we like s as a function of theta.
Yes.
So I relate y to theta. And you can do. So if you take the derivatives, you can get y dot and theta dot. You solve it, you get omega of this L-shaped link. Right?
Yes.
Now, because this L-shaped link is rigid, whatever omega you get for this part is going to be the same for this part. Now we're going to switch to this part. This is x of b, right?
Yes.
This is h, and this is theta. So you can relate theta to x of b same way, right?
Okay.
And then you can take the derivative and go, or maybe you can simply eliminate theta in the middle if that's easier, right? Get y of a and x of b in one equation and solve it.
Okay.
Does that make sense?
Yes.
Okay. So that was the good starting point. Any other question? We're good. Okay. So let's go back to the slides. If you remember Friday, and it was like the last 20 minutes of Friday, so half of you possibly were sleepy, half of you maybe didn't think well or whatever, tired. So I'm going to quickly review. We talked about instant center of zero velocity, right? Or sometimes as we call it, instant center of rotation. I gave you an example of, for example, your bicycle tire as it rolls, the point that contacts the ground, if it does not slide on the ground, which doesn't happen usually for tires, you can do it with your motorbike or car, doing drifting stuff, but for the bike, it's hard to do it, right? Specifically front tire. So this point rolls on the ground and does not slide, which means it has the same velocity of ground, which is 0. Now, considering this point of the tire has zero velocity, if I write the equation, for example, now we have it here. The vector analysis or vector equation between A and B, VB is going to be VA plus omega cross R. And because VA is zero, technically VB is like omega cross RBA, which looks like B rotates about A at this moment. Again, I repeat, this is momentarily. Few seconds later or like a few moments later, A is going to move up, another point is going to go down. That point becomes the point of zero velocity. So if you find a point with zero velocity, you may consider that at this particular moment, the entire rigid body is rotating about this point. So if you want to find velocity of any point, R of that point with respect to this space times omega. Like O, the velocity of O, RO times omega. The velocity of B, RB, which is RB respect to IC. We call this point with zero velocity instant center. Excuse me. And we show it with IC. So RB respect to IC is technically the radius of rotation about this temporary center of rotation. And that makes life easier. And you may realize that we could use this equation and write it for different points, but if you find IC, you can find velocity of any point quickly, find the R, find the omega, R omega the velocity. Any question about this? Okay. And I showed you this video. I'm not sure how visible it is, but consider this is like a wheel rolling inside another wheel. And when you look at the end, I brought this is not like fully related, but I brought this to show when they touch the surface, they have zero velocity. You see, it stops and comes back. Right? So stops like that. Now the question is how we can find IC. Considering the velocity is perpendicular to the radius of rotation. Remember, this is like rotation about fixed point, is not like permanently fixed, it's temporarily fixed, right? The IC has zero velocity, so it's like you have a pin on the IC and things rotate about that at that particular moment. So if you have velocity of 2 points, you draw the line perpendicular to the velocity because radius is perpendicular to the velocity for pure rotation. And the intersection of those is going to give you IC, right? Now, I'm going to switch back to the tablet and explain the other part. This is what we talked about, right? So if you find R, if you get the velocity to perpendicular line, this gives you IC. Now, if you want to find velocity of another point, you just draw the line. The velocity is going to be perpendicular to this, and the magnitude is going to be omega R. Now, the question is, sometimes the velocity of the 2 points that you are excuse me, dealing with are parallel. Let's say this is the same or one rigid body like a potato. This is point A. This is point B. This is velocity of A. And this is velocity of B. Now, you remember I said we draw a line perpendicular to this. and we draw the line perpendicular to this. Because these two velocities are parallel, the perpendicular lines sometimes coincide. Now the question is, which point of this is IC? You follow? So you have 2 points, point B, point A. They have velocities as I shown, and when you do the perpendicular, the two lines on top of each other. Now, to understand how we can do this, we're going to use the relation between velocity and omega. If I say VA is RAIC times omega, and VB is RBIC times omega, I'm going to divide these two. You're going to get VA over VB is RAIC divided by RBIC, right? The ratio of velocities is the same as the ratio of the radii of rotation. Any question about this part? Now that this happens, see what I can do. I'm going to draw a line from the end of velocity vectors. Just like that. And the intersection of that line and the perpendicular line, this is your IC. Why? Because if you look at these two triangles, please don't write for a second and just look at here. Look at the screen. Consider this triangle and this triangle. What do you see?
Using the midpoint rule to get velocity.
It's not midpoint, but what do you see? What do you see in these two triangles? One triangle is this yellow one, and one is the purple one, the light purple one, right? What that reminds you? Considering this angle is 90 degrees.
The ratio of two triangles.
Technically, they're two similar triangles, right? And if there are two similar triangles, the ratio of this to this is same as ratio of this to this. And that's what we have. So we kind of go backward from this ratio. We create the two similar triangles and find IC. And you may notice that this is the border of my rigid body, right? My rigid body is here. But IC is outside rigid body. Is it possible? Remember, this is how we assume. The IC is a part of the rigid body, but sometimes it may fall outside the physical boundaries that we see, right? So technically, this IC, this is still a part of rigid body, right? It looks like you weld something to this, and now everything rotates about this point. If you look at this example that we had last week, IC fell inside the rigid body, but sometimes it may, fall outside the physical boundaries that we see. And that's okay. The other case is you have the same rigid body, the two velocities, let's say this is point A, this is point B. The two velocities go opposite direction. Like this goes this way. This goes this way. Again, the velocities are parallel. So if you draw a line perpendicular to this and perpendicular to that, they fall on top of each other. We're going to use the same ratio and connect the end of velocity vector. Look at here. End of one velocity vector, end of the other velocity vector. I connect them. Right? And then this is my IC. This is RAIC. This is RBIC. These two triangles are still similar. This triangle and this triangle are similar. So this equation still valid. Right? Now let me ask you this question. Before asking a question, is the whole concept clear? Okay. Now I'm going to ask you this question. Assume that you have a rigid body. This is point A and has velocity of VA. This is point B and has velocity of VB parallel to the same thing. These are parallel. How I find IC for this? I'm going to draw a line perpendicular to this. And I'm going to draw a line perpendicular to this. Do they have any intersection? Technically, the intersection is at infinity, right? Two parallel lines theoretically or hypothetically meet at infinity, which means IC is at infinity, which means like RAIC, the length is infinity, RBIC is infinity, right? So if I find the omega of this object, omega is going to be VA over RAIC, right? And omega, you can use VB over RBIC, right? How much is this value for this case? Technically, VA divided by infinity and VB divided by infinity. How much you get? Come on, guys.
0.
0, which means there's no omega at this moment, which means this goes like a translation. And if it's translation, VA should be VB, right? So even for an object with translation, you can use IC. Theoretically, it gives you infinite radius and 0 omega. So you see the concept of, and these are perpendicular, obviously. The concept of IC is something you can use easily to solve problems. Any question? The only thing you need to remember to find IC you even don't need the magnitude to find IC. You need the direction of velocity for 2 points on the rigid body. Of course, if they are parallel, then you need the magnitude, right? Because you have to make this triangle. But if they are not parallel, you even don't need the magnitude to find IC. Now, if you have the two velocity, how you do it? Draw lines perpendicular. Two velocities. The intersection is IC. It's almost like a recipe. Any question? Okay. Now let's go back to the slides. This is what we just discussed. The direction of velocities, perpendicular, you get IC. If they're parallel, you create similar triangles. You draw a line from the end of velocities, then draw a line from the tip of velocity vectors. If they're the same direction, it goes like that. If the opposite direction, same thing. Now you see, in two of these three cases, the IC is outside the physical boundary that we see. This is still a part of the rigid body, which means it's like rigid body rotates about this point. Okay. And that is how we get these triangles. It's also true here. VA over RA, VB over RB. They're going to be omega. Now, remember, whatever we did here for IC was for velocity. There's no such a thing that IC for acceleration. If we go back here, for example, this point that has zero velocity, does it have zero acceleration or no? Let me ask you first. This point A here, or IC, not A, IC. This point IC, does it have zero acceleration?
Yes.
Okay. That was a brave answer. Let's analyze it. The point here has zero velocity. It has zero acceleration too, right? Does it even move? Remember, when acceleration is zero, the case is static. If it's a stationary, remains stationary, and if it moves, it's going to continue moving with constant velocity because acceleration is zero. So if this point has zero velocity and zero acceleration, it shouldn't move at all, right? Which means if this is the tire of your bike, you're standing somewhere, yes. But as this rolls, it has zero velocity, and then suddenly what immediately moves. Let's just look at this thing again. You see, stops but goes back. the velocity decreases, gets 0, and then increases. That means you have an acceleration this way. After the center point, the velocity keeps going down up to 0 and goes back, right? So 0 velocity doesn't mean 0 acceleration. I have another example for you guys. I showed it to you just at the very beginning of the lecture. Let me see. I'm not sure why the screen share stopped. The example we have here, look at this point A. Point A could be on the edge. I put it here, but see what happens. You see, when it comes to the lowest point, it stops but goes back, right? It has acceleration. So I see that the bottom line is IC is going to have acceleration, and you cannot find a point with 0 acceleration. I mean, you may find, but that's going to be, random somewhere. There's no procedure to do it. So we're not going to use IC for acceleration, only for velocity. I just want to highlight what we do here is only for velocity. Any question? Now, let's practice finding IC for some objects. If you look at this rigid body, technically there's like 3 parts. One is the roller A, one is the roller B, and the third part is link AB. If you neglect the size of rollers, consider it's very small, A goes down, so A is constrained to move up and down parallel to this surface. B is constrained to move parallel to this surface. Remember, I told you to find IC, we only need the direction of velocity. So A goes this way, B goes this way. To find IC, I'm going to draw a line perpendicular to velocity of A, which is perpendicular to this surface. Then I'm going to draw a line perpendicular to velocity of B, which is perpendicular to this surface. And that's going to be IC. And remember, AB has general motion. If it has translation, you don't need any of this. If it has rotation, it already rotates about fixed point. That fixed point not only is instant center, is technically permanent center of rotation. Look at this mechanism. It's like a crank slider. The piston goes back and forth with a linear motion here. Point B has rotational motion here. So the velocity of B is perpendicular to the radius, maybe going, if omega is this way, B goes that way. And the velocity of C is this way. So perpendicular to velocity of A is parallel to AB. Perpendicular to velocity of B is perpendicular to this guy. You draw the line, this is your IC, right? Remember again, the wheel B, or this blue thing, whatever you name it, has a permanent center of rotation. The piston C has translational motion, so everything has the same velocity. We usually use IC for a link with general motion. Any question? Let's try this example. You have a T-shaped link connected to the other 2 links, so AB, BD, CD, and BD is kind of like a T-shaped BDP. Excuse me. The problem says link A has omega of 8 radian per second this way. You want to find the angular velocity of link BD or BDP and the velocity of point P. And I'm going to use IC to do that, okay? While you draw this, I'm going to draw it on my notes. So you know that when you have omega of AB, you can find velocity of any point on AB, right? So, and that's what we're going to use. Okay, let's switch to the tablet. For some purpose, I'm not going to draw the T-shape part of this. It doesn't matter, right? We can draw it later, but I want to show you this is general approach. Now, to solve this problem, as you can see, it gives you omega of AB as 8 radian per second. It also gives you like LAB is 300 millimeter, LCD is 300 millimeter, and LBD is 600 millimeter. The angles are here 60 and 60. Okay. Now, can I find velocity of B using link AB? Yes or no? Oops. Someone say something. Can I find velocity of B? What kind of motion B has, by the way? Jake, you're very quiet. What kind of motion B has? Jake B. Let me just.
Is it translation?
B has translation. What kind of motion link AB has?
Pivoting off a singular point.
Link AB rotates about A, which is like a fixed point, right? So AB has rotational motion, which means B has a circular motion. And if that's the case, velocity of B is going to be RAB times omega AB, right? Sorry, not VAB, VB. Don't make this mix. We don't have VAB. We have omega AB, but for points, we only have V. Right? Now, the question is, what is the direction of velocity? Perpendicular to AB, which means if that's 60 degree, this should be 30 degree. Let me get rid of this B guy here. So if that's the case, velocity of B is going to be in this direction. Right? VB. Now, what kind of motion CD has? Link CD. We're talking about link CD. Come on, guys, this should be quick.
Rotational.
Rotational motion about point C, similar to AB, right? Now, do I know omega CD? No. But because it's rotational, I know that velocity of D is going to be perpendicular to link CD. So velocity of D, it's going to be something like this in this direction, right? You may realize that if this goes this way, this is going to go that way, and VD should be going down, but still it doesn't matter, right? We just need the direction. Now you guys tell me what kind of motion BD has. First of all, what kind of motion BD has?
General motion?
General motion, because I don't know if you can see my hands. You see, if this rotates like that, the pencil has general motion, right? A combination of rotation and translation. So if that's the case, I'm going to find IC. So let's find IC for link BD. What I need is 2 points with their direction of velocities. And those 2 points for me are point B and point D, right? I know the direction of velocity. What I'm going to do is this: draw a line perpendicular to velocity of B, draw a line perpendicular to velocity of C, and the intersection is going to give you IC. This is IC. Right? So this IC is for link BD. Right? And you may realize that it's falling outside the physical boundaries of link BD. But it looks like BD rotates about this point IC right now. Any question up to here? So I use link AB to find velocity of B. Now I'm going to use link BD. Now I'm going to ask you this question. Can I say the point B, the pin B that connects BD and AB has just one velocity? One point cannot have multiple velocities, right? Am I right? Hi, Z.
I think it's right.
Can I say point B has only one velocity value?
Yeah, I think it's right.
Right, because it's just one single physical point, right? Now, it doesn't matter if it belongs to link AB or BD or another link. It has one velocity. Now, if that's the case, I'm going to analyze velocity of B using link BD. because it's a part of BD, right? Then VB is going to be R BIC times omega of BD. Technically, what I'm doing is this. I look at the link BD, right? I look at this link. I say B is a part of this link, and its radius of rotation is this much, right? So this R times omega BD is going to give you VB. How much is this length, by the way? How much is this length? I'm going to write it here. RBIC. How much is it? Remember, these angles are 60. And this length is 600. Then how much is the length BIC?
600 as well.
600, yeah, it's just, what you call this triangle? I forgot the name. I never remember this.
Equilateral.
Equilateral, yes. Then if that's the case, this is going to be 600 millimeter. Same for this guy, RBIC is 600 millimeter. So, okay, I know VB from here. I know R, so I can simplify omega BD as VB divided by RBIC. And if you do that, 2.4 divided by 0.6 is going to give you 4 radian per second. That is omega for BD. Any question? Now that I found omega of BD, can I find velocity of D? Because D is also part of BD, right? So D rotates about IC. If that's the case, I'm going to go VD is equal to R DIC times omega BD. Sorry, this should be 2.4. Then you're going to get 0.6 times 4 is going to give you 2.4 meter per second. Now, if I want to find omega of CD, look at here for a second. Again, point D is a part of this guy and is a part of this guy. So if I use CD, I can find using link CD, omega CD is VD over RCD. And you put 2.4 times 0.38 radian per second. So technically, you can find omega of the other link too. Okay. Any question? So I'm going to review this a little quickly. Let me just clean this stuff here. So if you what we did was this. Please don't write and look at here. I had information on link about link AB, right? I found velocity of B from AB. Then I said, okay, B is a part of BD. I found IC, and from this radius, find omega. Then I said, okay, if I have omega, I can find velocity of D from this radius, right? And when I found this velocity, I said, okay, D is a part of CD, and I find omega CD. So you go from one point and kind of transfer information from one link to another. Does that make sense? Now, I just clean this a little bit. The problem also asks you to find the velocity of point P, which is at the bottom of this link. So if we do that, that was the middle. Oops. And then we're going to get I think it says 700 millimeters, so I'm going to go down by 700 almost. Okay, and this is point P. The question is how I find velocity of P. Can I say P is also a part of link BD? Is it? It's technically one piece, right? The problem calls it BDP. So, okay, if P is a part of link BD, if I use to find VP, use link BDP, right? The IC is for the entire rigid body, which means P rotates about IC at this moment. Remember, this is temporary, which means VP is R PIC times omega BD. Can I do that? Practically, this is the radius of rotation for point P, and I need to find that. This part is 700. I need to find this part. Okay, let's call this point M. So R PIC is ICM plus MP. ICM, if you look at this triangle, is going to be 600 sine 60. So 60 sine times 600, it's going to be 519.6 plus this is 700. So overall RPIC is going to be 1.2 196 meter or 1219.6 millimeter. If I do that, then simply omega BD, I already have it. VP is going to be 1.2196 times 4. And you're going to get 4.878 meter per second. These are final answers. Could I use another method like vector analysis? Of course, to do that, you have to relate. Let me give you a second to finish this. I'm going to explain. Are you guys done writing this? Everybody? Okay. Now, let's say this is link. Oops. This is A, B, D, and C. And omega AB is given. What could I do if I want to go with vector analysis? I'm going to go VD equals VB plus omega BD plus RD respect to B. You can get this equation, solve it to find velocity of D, right? And velocity of D is going to be RCD omega CD, because we know it rotates about 6 fixed point. So with this, you're going to find omega BD and omega CD. Writing vectors, cross products, IJ, separate them and solve it, you can do that. Now, if you want to find velocity of point P, you have to write this equation one more time. For example, VP is VB plus omega BD cross RP respect to D, respect to B. Do this one more time. This time, this is RP respect to D, B, and then solve this one more time. IJK products separate and solve it. So you see, to get this with the conventional vector analysis, you probably have to write 2 pages of writings to finish it, or maybe 1 page. With IC, I technically found VB, then get omega. This is like one line, one line, one line, and one line. So with 4 simple, multiplication, you can find all of the velocities, angular velocities you need. I guess now you may realize that why we did that, because it makes life, specifically if you are looking for multiple points. Now, if you want to go with acceleration, as I said, no IC for acceleration. You have to do all vector analysis, but for velocity, you can make it easier. Any question?
Can I use this example and relate to problem 51?
51, I think, asks you to do, and I would say no. Very good question. I would say no and tell you why. 51, first of all, is a part of absolute motion analysis. I want you to use the same method, right? The main reason, this is what you have, right?
Yes.
if you look at here, point A is not part of this rigid body, right? And neither is point B. So you cannot do it. A slides relatively here, B slides in this slot relatively here. You cannot do that. Right? So that's why it gives you that way. Good observation. Okay, let's go back to the, are you guys done with this thing? Yes. Okay, let's go back to the slides and do this example. This is quite interesting example too. You have two cylinders that could be like gears, same thing. As far as the two cylinders do not slide relative to one another, right? I don't know if you can see my hands. Let me just. When you have two rollers, you see the rollers roll. If there's no sliding and rollers roll, that point of rolling has the same velocity for the right and left object. For the gears, because of the teeth, they cannot slide, so it kind of roll, right? So the contact point has the same velocity for the two objects. Can you visualize this? Same thing with the tire on the ground. Rolls has the same velocity of ground. For the ground is 0. Here, the two roll, the velocity is not 0, but that is the whole concept. Now, the problem says you have omega of A, the disk or cylinder A. You do not have omega for the cylinder B, but the center of B is connected to center of A through link CD. And you have omega of CD. So AB rotates for itself. This guy, the link CD, rotates independently, but it forces the cylinder B to roll with certain, velocity. This is something we call planetary systems. Those who are doing ME are your ME students in the course mechanism. There's one part close to the end of the semester that we analyze planetary gears. That why they call it planetary? Because one is like a sun in the middle and the other one goes around it, right? That's how they call it. So omega A is given, omega CD is given. We are looking for omega of B. Let's see how we can do this. Let's switch to the slides. Did you guys took the notes about the numbers and everything? Okay. So then let's switch to the slides. So technically, you have I'm going to use the same colors, blue for A and kind of green for B. And I apologize if my circles are not perfect because there's no tool here to do circles. And then you have, let's say this is center for A, and this is center for B. And then you have the link CD. Okay, let's just do it by hand. This is A, this is B, this is C, and this is D. Omega A, omega CD, and the radius, this is RA, this is RB, RA is 0.2 meter, RB is 0.3 meter. Obviously, LCD is going to be 3 plus 2, 0.5 meter. Omega A, 6.25. Omega CD, 5 radian per second. These are the input, and we are looking for omega B. Now, if you look at this problem, we have three objects, A, B, and CD, right? What kind of motion each of these objects have? And I'm going to ask Haushin.
General motion.
For which one? We have three objects, all of them general motion. Do you see that link or cylinder A is pinned here in the middle, right? It cannot have general motion. What kind of motion A has?
Rotation.
Rotation. How about link CD? Link CD is also pinned here.
General.
It's pinned here, so C cannot move. You see, I don't know if you see my hand. This is like point C, right? Goes like that. What kind of motion it is?
Rotation.
Rotation about fixed point. How about B?
B. Rotation.
If it's rotation, this point should be fixed. Is it fixed?
Oh no.
No. Technically, if this is A, right? B is here, it's going to go here and here and here and here. So that's why we call it planetary. So kind of rolls around. The A looks like sun and B looks like a planet going around it. So has a general motion. It rotates and translates. So has general motion, right?
Yeah.
I think it's important to understand what kind of motion, what object or what link has, so we can follow. Remember, anytime you have a pinpoint, that's going to be fixed. Anything attached to that is going to have rotation. Now, if I consider B as the object with general motion, so cylinder B has general motion. Remember, we use IC for a link with general motion. Right? So we can use IC for B. To find IC for B, we need the velocity of 2 points. What those 2 points could be, which points those 2 points could be. And I'm going to ask Yi Yang. I need 2 points that I know their velocity. Which point I should pick?
I pick B.
Point B. B is the whole cylinder. This is the critical step to understand, to be able to solve the problem. Yoon, do you know which point I should pick?
Maybe E.
D? Point D, you said?
Yeah.
Yeah, point D is a part of, remember, again, the joints are the points that help us, right? Point D is a part of CD and also is a part of link B. Do I know its velocity? So let's just go one by one. So the first one, I'm going to go point D. Do I know its velocity? Callie, do I know the velocity of D, or can I find it somehow?
You can find it.
How?
You can use omega CD, and then can you use, like, I know you need a radius, but I'm not sure which one.
Okay, if you use, you almost completed it. Listen, if I'm going to use link CD and I'm going to use omega CD, this is the center of rotation, so the radius is going to be LCD, right? Let me just clean the thing. And you can find it. LCD is 0.5, omega is 5. So you're going to get 2.5 meter per second. Okay. And the way it goes, VD is going to be like this. Right? Perpendicular to the radius going up. And I need another point on the cylinder B that I know its velocity. Remember, we always go to intersections, interaction of the link with other links. That's how you get the points. What else I could use? Colin, do you have any idea?
So it has to be another point on B.
Another point on B that I know its velocity.
I'm not sure.
Do you know? Anyone? IZ, Andrew?
Could it be C since everything's rotating around it, so the velocity is 0?
Velocity of C is 0, but is C a part of disk or cylinder B? We are looking for 2 points, you see? We need two points. The 2 points should be on B. Let me just complete this. I said the intersection. What other objects B interact with? Does it interact with cylinder A? What is the interaction? Look at my hands. Rolls, right? So cylinder, let's say this is cylinder B and this is cylinder A. They roll on each other, which means at the contact point, which I don't know if you can see, at this contact point, there shouldn't be relative velocity, which means if I pick this point, I'm going to call it point M. Okay? The second point is point M right? Which is on the cylinder A and B. Can I find its velocity? I want you guys to pay attention here for a minute, please. See, when I found point D, I went to the other link to find its velocity. Now point M, I'm going to go to the other link to find its velocity. If M is part of A and rotates here, how I'm going to get its velocity?
The angular velocity and the radius of cylinder A.
Exactly. So you're going to get omega A times R A technically, which is 6.25 times 0.2, 1.25 meter per second. And the way that omega A is, look at here, the way that omega A is, Vm should go up. So technically Va goes up here. Now this is interesting. This is one of the cases that the two velocities are parallel and in the same direction. How do I find IC?
Wouldn't IC be infinite?
No, I'm going to use the similar triangles. So I'm going to draw a line from end of velocities. And I'm going to draw another line from the tip of velocity vectors. And of course, these are not perfectly accurate. Let's make it a little more realistic because that's how it goes. And if you draw that line, this is going to be your IC. What it means is this. If I separate, I let you guys draw this and I'm going to explain what it means. Are you done drawing and writing everything? I'm going to separate cylinder B and anything that relates to it, right? So that way it might be easier to. So I'm going to use this guys and move it down. I'm going to use this guy and kind of move it down. And then I'm going to take this line. Technically, this is disk B, right? With the velocities we know. And this is IC. It looks like at this particular moment, the disk or cylinder B rotates about this point. This is going to be RMIC. And this is going to be, what was the point? The RDIC. If I want to get the velocity relation, VD divided by R DIC is same as VM divided by R MIC, and this is going to be omega B, right? I can technically make two equations. Let's just separate it. So VD is R DIC omega B, VM is R MIC omega B, two equations. How many unknowns I have here? I don't know omega B, I don't know RDIC or RMIC because I don't know where this is. So I have technically three unknowns. Right? Look at the geometry of the problem. Can I get another equation? How much is this guy? One more time. This is the whole length of that guy. This is the length of this guy. This is what remains. How much is that? Let's just make it like a yellow. Or how much is this guy? Come on, guys. Kelly, tell me something.
RDIC minus RMIC.
And how much is it?
Not sure.
Someone tell me how much is it?
Just
This is-
RB.
It's
This is
part
the
two.
radius of B, right? This is the radius of cylinder. Equation number 3, you substitute, you solve it. Right? So technically, for example, you can get from here, RDIC is RM IC plus RB. You substitute here. So you're going to get VD is RMIC plus RB times omega B, and VM is RMIC omega B. If you eliminate omega B, you're going to get VD over VM is RMIC plus RB divided by RMIC. And if you get that, you're going to get 2.5 divided by 1.25 is RMIC plus RB, RMIC. This is going to be 2, which means RMIC is going to be same as RB 0.3. This is just a simple, problem. However you solve it, that's okay. And if you get that guy, remember we are looking for omega B. Now that I have this, omega B is going to be VM divided by RM IC 1.25 divided by 0.3, and you get 4 something. .167 radian per second. Okay. Any question? So if I want to review this, are you guys still writing? We're done. If I want to review this, you have one cylinder, second cylinder, and the connection. Things that you need to remember, right? The first thing is this point. Let me just go with this. This point belongs to both the link and the cylinder, right? So you can get its velocity. The other thing is the intersection of the two cylinder. If it's gear, remember, if it's gear, it's the same, right? Because gears definitely don't slide. But when it says there's no sliding in the roll, so these 2 points have the same velocity for these two objects and these two objects. That's how you get it. The rest is just the basic things we talked about. Okay, this is one velocity, this is another velocity. You get the lines and triangles and everything. So this was an example of having rolling objects, of having parallel velocities, right? And the previous example, this was simply two velocities, perpendiculars, finding IC. So we kind of cover both cases. Again, this is the joint of the two links. This is the joint of the two links. It has the same velocity for both links. That's how you relate them. Even if it's not IC, even if you want to go with this vector analysis, we still know that D and B belongs to both links. B belongs to this and this, and D belongs to this and that, right? So that's how, these are the things you need to remember. I explain it and it may just get lost, within the other explanations. So I repeat it now. These are the things you need to pay attention, okay? Any question? We have 25 minutes. By the way, we don't cover this part of the chapter. The last part of the chapter, I'm not going to cover it. Okay. But we can start chapter 17, or we can do one more example. Which one you prefer?
Probably one more example.
I knew the answer already. Yeah, absolutely. Okay, let's do this example. Here you have omega AB is given, or no? Let me see. Omega AB is not given. The velocity of block is given. So you know the velocity of the block going up with 12 inches per second. You have all the dimensions, and we go from there. So let me draw this thing here. So the first question is to analyze to see what kind of motion each object has. The slider C obviously has translational motion, right? Going up and down. The link AB has rotation about fixed point. A is fixed. And the link BC has general motion. So if we want to use IC, which link I should pick for IC? Come on, guys. Which link I should pick for IC? I explained it a couple of times that which link we go.
I think link B.
Sorry, I couldn't hear.
I think link B.
Link B?
Yeah.
B is not a link, B is a point.
Oh, yeah, I mean point B.
Link BC, right?
Yes.
Link BC that has general motion, we're going to pick that to find the IC. Okay. I need the direction of velocity for 2 points on link B, link BC. One is point C that, as you can see here, goes up. So I'm going to draw a line perpendicular to velocity of C. Perpendicular to velocity of C is going to be perpendicular to that green line, right? So I'm going to draw a line perpendicular to this. And the other point is B. What kind of motion B has? Aaron, what kind of motion B has?
Vertical.
We don't say vertical in terms of translation, rotation, general motion.
Translation.
B has translation. Look at one more time. B is a part of link AB.
Wouldn't B also be general motion as well?
Good question. General motion is for the link, right? B is a point. B has like rectilinear, you know, like rotational motion, circular motion, linear motion, things like that. B, if it's a part of AB, B rotates about fixed points, right?
So it's rotational.
Is rotational, is a circular motion. So B rotates about fixed point A. And if that's the case, let me go to the slides. Oh, sorry, to the tablet. You see, I said the first thing is velocity of C. C goes up and down. Perpendicular to that velocity, it's going to be a line perpendicular to the green line. So that is one line, okay? The other thing is velocity of B. Velocity of B, if B rotates about fixed point, which is rotating about A, its velocity is going to be something like that. Its velocity is in this direction. Perpendicular to velocity, it's going to be perpendicular to this guy. And interestingly, I mean, let me just change the color because that's not visible. I'm going to go with the dark purple. Okay. Therefore, this is your IC, which means it looks like the link BD temporarily rotates about this point, right? So I need to find this length and this length. Okay? So let's clean the thing. I'm gonna move, okay. We need to have all the angles for this triangle. How much is this angle here? Please do not write for a second. Just look at here, answer this, because this is the important part in this. It's just more geometry. How much is this angle?
30 degrees.
30. How much is this angle? And be careful when you answer, whoever answers that.
90.
It is not 90, definitely. How much is this guy? Huh? This is a small angle. How much is this guy? 30. How much is this guy? 60. How much is this guy? 45. So technically this is 60 plus 45, right? $60 plus 45 is 105. And if that's 105, this is obviously 45. Right? So we have a triangle. I draw it roughly here. This length I know. This is 4 inches. Right? So this is 4 inches. This angle is 45, 30, and 105. And I look for, let's say, ICCB. How do I find lengths IC? C and ICB. How do I find it? Come on, guys.
Law of cosines.
Law of cosines or law of sines?
Cosines.
For the cosine, you need 2 sides. I only have 1 side. For the sines, you need 2 angles. I have all 3 angles. So technically, I can write BC over sine 45 is ICC over sine 105 equals ICB over sine 30, right? And I can separate this into 2 equations. One is BC over sine 45 equals ICC over sine 105 and BC over sine 45 is equal to ICB over sine 30. From here, you can get ICC, and from here, you can get ICB. I want you guys to get these numbers for me. if you solve them, you should get these numbers. And let me know if you got the same numbers.
I got the same numbers.
Okay, good. So we found the radius of rotation about IC, right? Now, again, I'm going to start. Let me just stay around here and erase these things. I'm going to start with the point that I know its velocity, right? So practically, if I use link BC, VC is going to be R IC or ICC, doesn't matter, times omega BC. Can I do that? Again, look at here. I assume C is a part of BC. So it rotates about this point, and this is the velocity, right? If that's the case, from here, you can get your omega BC is VC divided by R I. Remember, CIC or ICC is the same, right? It's just a length, doesn't matter which one comes first. And if you calculate this, you're going to get 12 over 5.464. And that is going to be 2.196 radian per second. This is omega BC. Now I'm going to switch to the point that I am looking for, and that point is point B, right? For point B, I can write the same equation. VB is R BIC times omega BC, because remember, B and C are a part of link BC. Then you're going to put 2.196 times 2.828, and that should give you 6.211 inch per second. So I use link BC, got two velocity equations using IC and solved it. Now problem asks for omega AB. How I get omega AB? How I get omega AB? To find omega AB, of course, omega AB is for the link AB. I have to analyze link AB. We consider link AB and the point that I have some information, and point B. Remember, the whole purpose of finding velocity of B was to be able to use it for link AB. Now, if that's the case, I'm going to get VB is RAB, omega AB, and from here, omega AB is VB over RAB. You put the numbers 6.211 divided by 4. I think the length was 4. Let me check. 5. This is 5. And then omega AB, will be 1.24 radian per second. I want to show you the process again. It give you like a minute to write down these numbers. It's almost all of the problems look similar. Are you guys done writing? Please pay attention to the screen for a second. Everybody. So I look for the link with general motion, right? I find the IC. That was the first part. Those sine theta, blah, blah, that was just for the geometry part to find the length. Each problem is different, right? Sometimes you just get L cosine theta, L sine theta. Sometimes you go with triangle, whatever. Then the next step is to use the point that I have information about. I know VC. I relate VC to omega BC and link BC. I find this omega. Then switch to find the velocity of By, because B belongs to AB, and this is what I'm looking for. So I switch to point B, find velocity of B, and then switch to link AB. So from BC, C, then AB. And that's kind of similar with other problems. You start from one side that you have information, go to the rigid body with general motion, then switch to the other link. It's kind of like a chain of transferring information. Okay? So I hope these 3 examples gave you enough idea. Your homeworks are due when?
Saturday.
Saturday. Okay. We can have a quiz this Friday before the homeworks end, because if we do that, then we can have another quiz next week, and then we're going to have the final exam the week after. Okay. I usually try to have the quizzes after the homework deadline at least, but if we do that, we're going to miss one quiz. It's up to you. If we do it next week, it's less likely to have another quiz, or we have a quiz on Monday and another quiz on Friday next week. Which one you prefer? Say something. If you don't say anything, I'm going to ask Callie, who represents the 51%.
I
I like
feel
to have,
Oh.
I like to have the answers to the homework before we do the quiz. So I don't know.
I agree with that. I feel like it would be nice to go over like the homework solutions before the quiz.
Okay. Then we're going to have a quiz on this chapter next Monday. Okay. And it's likely that we have another quiz next Friday. Something like that. Because I don't want to give you a quiz. I mean, I can give you a quiz the week after and the next Friday. We're going to see how it goes. Okay. So we're going to have the quiz next Monday. And on Wednesday, we're going to start a new chapter. Please make sure you solve the problems yourself. If you need help, I recommend you to review these videos that I explain, because, you know, I explain almost every details, right? I'm not expecting when I say all of these things, you absorb it immediately. But believe me, if you get stuck, watch the videos again. You don't have to watch the entire 2 hours video. You can, you know, fast forward to the problems and see how we do it and my explanation. If you still need help, which is okay, let me know. We can meet in the Zoom office hours, cover that, because as I said, this is the critical chapter for you guys as mechanical engineers or even as mechatronics engineers. There's a lot of information here that will move forward to the next courses. Did you guys enjoy the lecture? Really? Okay, good. I'm gonna post this video sometimes today later, okay? And we go from there. Meanwhile, if you have any question about any part of the course, remember, we are close to the end of the semester, but I mean, it's a very short already. If you have any suggestion how we should deal with the questions, with the lectures and everything, let me know. We can make adjustments. We still have like 2.5 weeks left. So we can make adjustments that matches your preference, okay? Feel free to contact me about anything related to the course, okay? Thank you all and see you on Wednesday. Have a good rest of your day. Bye.